Okay, so this is the third part of the topic 1, physical quantities and units. We're getting into the most difficult part, which is into vectors. Okay, now vectors are important in physics because a lot of motion and so on has direction associated with it. And that's essentially what the definition of vectors is all about. We've got two types of things here. We've got scalar and vector. Scalar is essentially a magnitude without direction, whereas if we're going to look at a vector is something that has a direction. So, what is a vector? Well, a vector is a magnitude. There's something that has a magnitude with a direction. Okay, well, these are not the proper definitions. Please, can you find a better one using a dictionary? So, what we have here are some examples of some physical quantities. We've got speed, mass, temperature, intensity of light, distance, time, energy, force, acceleration, displacement, velocity, and momentum. So what we'll do is let's just have a look at a few. Now, speed is something that doesn't matter which way you're going. You could be going left or right. The value is always going to be the same. There's no negatives associated with it. It is just the same no matter what way you're going. However, there is velocity, which is essentially the same thing. It just has a direction that is important. If I said that I was going plus 10 meters per second, it is in fact opposite to someone going negative 10 meters per second. They're in fact going opposite directions. So, two different things. Let's look at another comparison there. How about mass? Now, mass is scalar. Doesn't matter which way you're moving or whatever, your mass doesn't change. However, weight, which people usually associate with mass, is actually a vector. It's a force. It has a certain direction. So let's put force in here as well, because it's the same as weight. Let's look at something like temperature. Temperature doesn't matter which way you're going, and so on. Okay, distance, and there's actually a distance term associated with being a vector, and that is displacement. Okay, and I'll leave the rest up to you. Now here's some vector examples. Displacement, you could be going 12 meters upwards, it could be 12 meters to the right, 12 meters to the left, doesn't really matter. So there's some examples. You notice that all of them have some sort of direction associated with them. You don't always have to write the direction for a lot of stuff. It's implied by the diagram or so on, depending on what you're looking at. How do we draw vectors? Well, we draw an arrow. The length of the arrow denotes the size of the vector, and you must give it an angle because it is a vector. Okay, so these both have direction. Let's have a look at some simple addition of vectors, so some mathematics. So what you can see here is we've added the two 5 vectors, both going the same direction. So we add the two together, we get this 10. Now how do you actually do it? Well, you add vectors head to tail. Okay, so you always add head to tail. Okay, and then the final vector from initial tail to last head. Okay, so see there with the 10, I've added the two 5 vectors head to tail there, and then the resultant goes from the very first tail to the very last head, and it's shown with a double arrow. Mathematics-wise, that's just 5 plus 5 because we're in the same direction. Here we've got a negative showing an opposite direction. So, because that's a negative there, 5 plus negative 5 in fact makes 0. And if we try to add these two things together, so there's the vector going forwards. If I add the other one going this way, there's no room to draw a resultant. If I look at the next one here, 5 plus 10, okay, essentially I just move this vector forwards a bit, add it to that one, my resultant looks like that, and it must be 15. This one here, it's going to be 5 forwards. So if I put the 5 forwards there, okay, I've attached it to the tail of the negative 10, and now if I draw the resultant from the initial tail, which is the one of the 5, and I draw it to the final head, I get a resultant there of minus 5. Now, hardly ever we're going to use vectors that are as simple as that. Generally, they're going to look something like this. Okay, we're going to have two vectors, in this case, A and B. Sorry, rather wrong way. A and B, and we're going to add the two together to find some sort of resultant. The difference being in this case is this angle. Okay, there's an angle which will change it. So, look at the next one here. How do we add them? We add them either with that parallelogram we just had on the last page, or, okay, the other way of adding vectors is using the one that I like using. Instead of drawing the whole parallelogram thing, we just use this one here, which I've just already mentioned with the other one. Even if your vectors are at angles, even if your vectors are at angles, like in this case here, there's an angle, then you can simply just put the next vector head to tail and then draw the resultant from the first tail to the last head. So let's have a look at this in action. Okay, so I've got two vectors here. I've got A and B. I can move these around. I'm keeping the same angle. Okay, I'm not changing the angle at all. And I can then attach it to the tail of B, and then I just draw the resultant from the first tail to the last head. Okay. Now the good thing about this is it doesn't actually matter what order we put these vectors in. As long as you keep the same angle and the same length of vector, it does not matter. Okay, so it's very, very important. And you can see that the vector A plus B, the final resultant vector, always goes in the same direction. And it happens for more than one vector. Usually it's hard mathematically to answer something with more than just two vectors, but you can draw it. Okay, so here we've got A, B, C, and D. So if I add all these head to tail, and head to tail, just like this, and I draw a vector from the very first tail, which is there, to the very last head there, that will be my resultant. So there we go. Now, like I said before, doesn't matter what order we put these in. Oh, try to get that one out. So let's say we do D first, maybe B, then maybe A might go up too far. Let's try C, goes down there, and then A up there. If I'd done them nicely, we would end up at the same place. So it doesn't matter which order you do it in. A couple of things here about relative velocity. Essentially, relative velocity are if two things of the same type are added together. Remember, for homogeneity, you have to add the same things. Then you can get a resultant vector that means something. In this case, imagine we had a plane heading down. So we've got a plane flying downwards here. And this is the speed of the plane. Let's say it was going 200 meters per second, and there was a wind going 20 meters per second to the 90 degrees to the left there as it was going down. Then it would actually head off in that direction there, the resultant. And if you measured the length of this, you could actually find out what his resultant speed would be. And the same sort of thing happens here. If the wind was going the other way, you'll head off that direction with a certain speed. If the wind was going straight down in the same direction, or a tailwind, and let's say the wind was, the plane was doing 200 and the wind was 20, well, the actual final velocity of the plane would actually be 220. Okay, remember you can only add the same units though. Here's another example of addition of vectors. Two ropes are tied around a tree. A force of 500 newtons is applied to each rope. Calculate the total force applied to the tree. The forces act in the same direction. Just imagine two people pulling on the tree with the same force. So each of these are pulling with 500 newtons. Then that's going to have a combined force in one direction of 1,000 newtons. Okay, so if I did the resultant of these two, I end up with 1,000. In other words, I grab the vectors, so this vector here, add it head to tail, then it will double in size and end up being equal to 1,000 newtons. Here we've got two ropes tied around a tree, and this time they are at right angles to each other. Now you're not sort of helping each other perfectly. You're not pulling in the same direction and helping each other perfectly. This time there's sort of a bit of sideways force that is not really giving you extra help. So we've got two vectors here. Let's see if we can change colour. Oh, maybe not. Let's try this. So 500 newtons and 500 newtons. Okay, so I've got the two vectors there. Now, if we want to add these two, remember what you do? You move one of the vectors so they're head to tail. So remember, so it has to be head to tail there. So just for the convenience of this drawing, I made one earlier. Here is a vector that has been moved from there to there. So let's call this vector A. This will be A dash. Okay, so I moved it over to there. And then the very first tail, which is here, it's the first tail, to the very last head, you draw the resultant vector there. Now, if you have a look at this, okay, that's 90 degrees. You've got equal sides on this triangle here. That's 90 degrees there. These then must be 45, 45, okay, and you should pretty much know what that final result is equal to. And you should actually write an angle too. So it's 45 degrees below horizontal or something in this case, even though we're looking down on it. It's not really the best way of explaining it. So here we go, a different one. We've got these two forces are now an angle of 60 degrees to each other. Same thing as before. Move the vector like that, and you can then just add the two together to get a resultant there. Okay. So, how do you find that? Well, you can either use a scale diagram or you can use the cosine sine rule if you know what they are. Now, let's have a think about these angles. Oops. Let's have a think about these angles. If this is 60 degrees right around there, we move this one up to there, then have a think about this one. This one now would be essentially 30 degrees. That will be 30 degrees, and that will be 120 degrees. So you can go from there. One easy way would to say that 100 newtons equals 1 centimeter, and then draw it. Okay, and you'll be able to find the answer. And here's the answers. Now this is the most important part of vectors. Essentially, if you want to do something that involves change, you must do subtraction. Okay, change means final minus initial. Okay, so when you're looking at things like vectors, you must actually take your final vector and minus it from the initial vector, being aware that things like angles, directions are very important. So it's easier to show you by example. So to subtract a vector, we're going to add the negative of the vector. Okay, we do vector addition by diagram. We can't actually do subtraction, but by doing a simple trick of making one of the vectors into a negative, for example, in this case we have positive b. If we make it a negative b, we can add it to a. But be aware, the order is important. Okay, the order is important. It's why people sometimes get the wrong gradient, negative or positive, because they haven't done the right order. So, for example, here we've got A and B. Now, what we've done is you make a negative B. In other words, you turn this B vector around. Okay, so it has this arrow going the other direction, and then you just add them like you would any vector. So, for example, what we have here is a ball strikes a wall at 10 meters per second, bounces off at 10. Okay, perfectly elastic. Strikes the wall at 90 degrees. Now, we have two vectors here. This one here, the blue dots down it, that is the initial vector, okay, initial velocity. What's the size of it? It's 10. Sorry, keep using that blue, it's not good. 10 meters per second, and the other one is 10 meters per second as well. You could say it's negative, something like that. Now, remember change. What is the change? Very important. Change is final minus initial. Okay, so if I'm going to have final minus initial, that's going to be the same as final plus negative of the initial. So let's make that initial one into a negative. There we go. So now I've got two vectors going in the same direction. If I add these two vectors now, like that, I then get a final resultant going that way, away from the wall, of a value 20 meters per second. So the answer is equal to 20 meters per second away from the wall. The way of thinking about that is initially this ball is going 10 meters per second. Okay, it's going 10 meters per second here, hits the wall and stops. Okay, so it's gone from 10 to 0. It's actually slowed down, so it actually means it's got a negative 10 change. It then speeds up in the negative direction. Oh, if I can get it again, see? Maybe not. So it then speeds up in the negative direction this way, up to a speed of 10. So that means it's gained a speed to negative 10. So it's gained a speed, change of speed of negative 10 there. So in total, we get a change of negative 20. When you got things at angles, a little bit more difficult. Okay, so let's have a look at this. 45 degrees from the wall, bounces out 45 degrees. Okay, so that means there must be 90 degrees between these two. So there's 180 in total. Okay, so it must be 90 degrees between the two. So that must be a 90 degree triangle. Not the best diagram here, so maybe we just adjust a little bit. Okay, like that. Now, when this ball comes in, bounces, what's the change of velocity? Final minus initial. Okay, so let's make a negative of the initial. There's a negative of the initial. Let's give it the right angle. There we go. And now move it down there so it's head to tail, and then let's draw in the resultant. Oh, because I changed it, change the size, let's just move it down. Okay, so there you go, there is the resultant. Essentially going straight out of a certain size. How do you find that size? Well, we know that each side of this triangle is 10, 10. Okay, what are the angles? Well, if that's 90 degrees there, then this must be 45. Okay, this must be 45, and then you got 90 there. Here's some answers for that. Now, last thing here, vector components. Vector can be represented by two perpendicular components. Okay, in other words, if you have any sort of vector, if I just draw a vector there, okay, if it was nice and straight, it would be much better. If I had this vector, no, it doesn't recognize it. If I had that vector there, it will have two components. It will have a horizontal and it will have a vertical. And it's always in such a way that this vector here is the hypotenuse. In other words, if I move one of the vectors across to there, if I move this guy across to there, then the pink one is the hypotenuse. It's always going to be the hypotenuse. So in this case here, if I had a vector x and I want to find the horizontal vertical components, then I use x cos theta or x sine theta. So this could actually be an f vector. In that case, it would be f cos theta or f sine theta. So example here, after takeoff, an aircraft climbs at a rate of 150 meters per second, an angle of 30 degrees to the ground. What are the horizontal and vertical components of its velocity? So essentially, there's the ground. It's got its vector this way of 150 meters per second. Okay, and it's got an angle there of 30 degrees. And if you just work out, you can just work it out by using the formulas that we just looked at for sine and cosine. Okay, so let's just have a look. So we've got 75. So all I'm doing here is doing 150 times cos 30 and sine 30. Okay, so it's 129.9. So, let's make that 130. So this one here is the horizontal component, and this is the vertical component. Now, to give it some meaning, how far along the ground would it travel in 200 seconds at this angle and speed? Well, it's traveling 130 meters per second along the ground. So this one here is 130 meters per second along the ground. It's rising at 75 meters per second. So if we just do here, how far? So displacement equals VT. So it's going to be 130 times 200 because that's 26,000 meters or 26 kilometers. Okay, in the vertical direction, same formula. Okay, so vertical direction we're going at 75 multiplied by 200 gives us 15 kilometers up. Okay, probably not true, seeing they all fly at about 10 kilometers. Okay, thank you.